Okay, so I'll start now. So today we'll be learning about orbits. Um, so first of all, what is gravitation? Gravity is the force that attracts masses together. And in the example here, we see an apple is falling off a tree. And we can say that there's gravity because the apple is falling down and the apple is attracted to the earth. So Newton came up with the formula for law of gravitation, which is force is equal to G. Oh, wait. So force is equal to G times a mass of one thing times the mass of another thing divided by the distance squared. And the constant G is 6.67 times 10 to the power negative 11. And the units for that are newtons times meters squared over kilograms squared. And if you plug that into the equation, you get newtons times meters squared over kg squared. And for mass 1, it would be kg, and mass 2 would be kg. And distance for the masses squared would just be meters squared. So you can cancel that out, and you would be left with newtons for the unit for force. Okay, so now Newton proposed that every object attracts every other object with a force in like the entire universe. So something on Earth could attract something in outer space, but the force must be inversely proportional to the square of the distance between the objects. So it would be proportional to 1 over r squared. And it would be directly proportional to the product of the masses, which is the mass of one thing times mass of two things. So, and then you can also write the formula for G, which is the acceleration due to gravity. So if you're trying to find the gravity on the moon, for example, then you could, since the original equation would be F is equal to G times M1 times M2 over R squared. So you can write F as MA, and it would be MA is equal to G times M1 times M2 over R squared. And for example, we can have the mass be equal to like the mass of the moon, and the other mass could be equal to the mass for the force. So you can cancel out this mass and this mass. So you'd be left with A is equal to G times M1 over R squared. And A would be just G with acceleration due to gravity. So you would get G is equal to the gravitational constant times M over R squared. And for the moon, if you want to find the acceleration due to gravity, you would just plug in the value of G, the mass of the moon, and the R squared, which is in this case would be the radius. And you could also do the same for Earth. So we know that the for Earth, the acceleration due to gravity is just 9.8. And you can prove that by just plugging in all the stuff for the equation. Oh, another thing is, let's say that you're on a cliff and you're shooting something off the cliff, such like a bullet or something. It would eventually fall to the ground, like with any velocity or distance, except if the velocity is extremely high, then it could go out of orbit. So it would leave the Earth and like orbit it instead. So, and then you would try to find, and for that, you would need, that would be the escape velocity. So let's say a rocket, for example, is leaving Earth. you would need to find the escape velocity to see how fast we need to go in order to leave Earth. So you could use the um, energy conservation. So it would be K initial plus the initial potential is equal to the final kinetic plus the final potential. So if you're leaving Earth at extremely high speed, then let's just say that it would go to an infinite distance. So this final part would just go to 0. And for the initial kinetic, let's just say it's 1/2 times m times the escape velocity you would need. So it's v squared plus escape. And then plus the potential, which would be mgh. And for g, you could write that as in this equation g times m over r squared. And you can cancel out the m's would be, oh no, you cancel out the h. One of the h's would be g times m squared over r. So it would be negative g times m squared over r equal to 0. So you can do that and find the velocity. And you can see that in this example right here. An example of gravitation. And you can look that for a minute. So you can see that it asks, what is the force of gravity from Jupiter on you at birth compared to the force of gravity from a nearby Coke machine? So in this example, you weigh 3,000 grams and the Coke machine weighs 10 to the power of 5 grams. And the distance between you two is 10 centimeters. And for Jupiter, it weighs 1.9 times 10 to the power of 30 grams. And the distance is 8 times 10 to the power of 13 centimeters. So if you wanted to find the force between each of you separately, for the Coke, it would be G times 10 to the power of 5, which is the mass of the Coke machine, and times the mass of you, which would be 3,000 Gs, divided by the distance squared, which is 10 centimeters squared. And if you want to find the force for Jupiter, you would do G times 1.9 times 10 to the power of 30 grams times your weight, which is 3,000 grams, divided by the distance, which is 8 times 10 to the power of 13 centimeters squared. And the force of gravity is larger for you from the Coke machine because if you're closer, so the force is stronger. And now we can talk about circular motion. So circular motion is, for example, when in this picture right here, you're rotating or like spinning a ball above you. So in this diagram right here, you can see that the acceleration is going inwards and the velocity is perpendicular to the circle. Because if you're moving in circular motion, then it's going to be a perfect circle. So the important thing about this is you get so you realize that the centripetal acceleration would be equal to the velocity squared over the radius. And another important concept is the centripetal force. And so you know that force is equal to mass times acceleration. So you would just plug in the centripetal acceleration, which is m times v squared over r. So the centripetal force would just be mv squared over r. Okay, so And next we'll talk about orbits. And there's three laws that Kepler made for orbits. And the first one states that the planets follow elliptical orbits around this. And for example, if the sun is at one point, then, and let's say Earth is at this point, then the Earth will follow an elliptical shape instead of a, a circular shape. And I won't get into the math about that right now. You guys can research that on your own time. And next, for Kepler's second law, it relates speed and distance. So as you see in this diagram, these periods are, this is, so basically, a planet is rotating around the sun. And for this period right here, then it's 1 month, and this period is also 1 month. And these two vectors right here have the same area, but you can see that they don't really look like they have the same area. So so Kepler made it to, so it's that the farther away the planet is from the sun, the slower it goes. So it's going slow like over here. And as it's approaching the sun, it gets faster and faster. So it's the same amount of time and the same amount of area. So that shows that the planets don't always have the same velocity when it's orbiting the sun. And the next thing is Kepler's third law. And for the diagram, you can write the sun here and the Earth here. And it's going in on orbit as well. So if it has a centripetal force and a gravitational force, you can say that the centripetal force is equal to the gravitational force. And the centripetal force is mv squared over r. And the gravitational force is g times ms, which is the mass of the sun, times m of the earth, mass of the earth, divided by the distance squared. And the mass here, since it's the earth, would be the mass of the earth. So first of all, you can cancel out one of the r's and the mass of the earth. So you're left with v squared is equal to g times mass of the sun over r. And for circular motion, v is actually equal to the distance over time. And the distance would be 2 pi r. And the t would actually be the period. And I won't get into that right now, but it's 2 pi r divided by t. So if you plug that in, it'd be 2 pi r over t squared is equal to the g times mass of the sun over r. I'll write that again. So if you expand that, you get 4 pi squared r squared over t squared is equal to g times ms over r. And you can, if you want to find t, then it'd be 4 pi squared r squared equals g times mass of the sun over r times t, and then be t squared. T squared equals 4 pi squared r squared times r divided by g times ms. So it would be equal to 4 pi squared times r cubed over g times ms. And it's the same equation as this equation, but this is the square rooted. So there's a relationship between t squared and r cubed. And I think, and you can apply this to satellites orbiting the planets to find their period around the Earth. So this is example number 2. And you can see it says find the altitude above Earth's surface where a satellite orbits with a period of 1 day. Note that the radius is 6.37 times 10 to the 6 meters, and the mass of the Earth is 5.97 times 10 to the 24 kg. And they give you the period is 1 day, or 8.64 times 10 to the 4 seconds. So if you're trying to find the altitude, and you can use the Kepler's third law, and it gives you right here as that. And if you're just trying to find the radius, you can write in this form. I mean, the distance. And so if you plug in all the values, you get 4.22 times 10 to the power 7. And if you're just trying to find the altitude, then it would be r minus the radius minus this distance right here. So you can just get that value. Okay, so you can do question number 1, and you can have like 1 minute to do it. Okay, so I'll explain the question now. So it asks a ball of mass of 1 kg on a string is rotating about the center axis with a velocity of 3 meters per second. If the tension of the spring is 15 newtons, what is the radius of the circular path of the ball? So you're given that the force is 15 newtons. So you can just plug this into the equation. F equals mv squared over r. And F is 15 newtons. Mass is 1. The velocity is 3 squared, and r is r. So you can do r is equal to 9 over 15, 3 over 5, or 0.6 meters. Any questions? And here's your solution. And you can do the next question. Okay, so I'll go over the question now. So it asked, the moon's distance from the center of the Earth, of the Earth is decreased by multiple of 3. How would this affect the gravitational force of the Earth on the moon? So you would still write the equation F1 equal to G times M1 times M2 over R squared. So if the center, if it is decreased by multiple of 3, then it would just be 1/3 of R and squared. So if you, that would be 1/9 times R squared, and 1/9 be written on top as 9 times G times M1 times M2 over R squared. So it wouldn't be a decrease of by a factor of 9, it'd be an increase of factor of 9. So it would be easy. And here's a solution. So, okay, so um, again, escape velocity is from the energy conservation, so it would be K initial plus gravitational initial equal to 0, and the K is 1/2 m v escape squared plus negative g times m times over r. So you can tell someone that equals 0. So you get v is equal to root 2 g m over r. So now you can just plug in the stuff you're given. So it would be root 2 times g times 3.21 times 10^23 divided by 8.53 times 10. So okay, so now I can do question 4 and 5. Here's the solution again, if you didn't see it. Okay, so now you guys can do question 4 and 5. Okay, so I'll go over the question now. So it asks two asteroids, one with a mass of 7.12 times 10 power 18 kg, and the other with a mass of 5.33 times 10 to the power 8 kg, and it's that distance apart. What is the gravitational force in the larger asteroid? So you could use it. You use the equation G times times m over r squared. So it's be G times 7.12 times 10 power 18, and then times 5.33 times 10 power 8 divided by 10 times 10 power 10 squared. And that's for the larger asteroid. And for the smaller asteroid, it would still be the same since nothing's really changing. So it would also be you would use the same equation and you would get the same answer. So here's the solution right here. And here's the next question. Okay, for this question, I didn't really talk about this, but the ratio of the two for Kepler's third law, it's t squared, ratio of r cubed. And you can also write that as t2 over t1 squared is equal to r2 over r1 cubed. So for like, if you have a ratio problem like this one. Okay, so I'll go over the question now. So it asks, so it says Titan is the largest moon of Saturn and has a mean orbital radius of 1.22. That's actually 10 power of 9 meters. Oh, sorry about that. And the orbital period of Titan is 15.95 days, and Hyperion is another moon of Saturn, has an orbital mean radius of 1.48 times 10 power of 9 meters, and asks what the um, orbital period of Hyperion is. So if you use this ratio right here, you can write T Titan over T Hyperion squared is equal to the radius Titan over um, the mean radius of Hyperion. So it would be 15.95 days divided by T Hyperion squared is equal to 1.22 times 10 power of 9 divided by 1.48 times 10 power of 9 meters. And this is cubed. So we can just do the math and find the orbital period for Hyperion in this solution. Okay, now if you guys can do questions of them. Okay, so for this question, it's Oscar asking for how many years would it orbit, how many years would it take for this planet to orbit the sun if the mean distance was 4 times that of Earth? So you could write, you do t squared over r cubed, and you would get t1 squared times r1 squared is equal to t2 squared times r2 squared. And that's in the other equation. We got that showed like t1 over t2 squared is equal to r1 over r2 squared. So t1, let's say, is 1 year, and the radius, that equals to t2 squared times 4 r2 squared. So you would get, you're trying to find t squared would be r squared over, wait a second. Um, oh, sorry. It would be cubed. So it would be r cubed over 4 r cubed. So it would be 1 over 64. So it'd be t squared equal to 1 over 64, and t would be equal to 1/8. And since it's 1/8 as long, it would be 8 Earth years. So here's the solution. All right, so you do question 8. Okay, so for this question, um, it gives you a lot of information. It says the Earth and the Moon attract each other with the force of gravity. The Earth's radius is 3.7 times of the Moon, and the Earth's mass is 80 times greater than the Moon's. The acceleration due to gravity on the surface of the moon is 1/6 the acceleration due to gravity on the Earth's surface. If the distance between the Earth is decreased by a factor of 4, how would the force of gravity between the Earth and the moon change? So you write force is equal to G times M Earth times M moon divided by R squared. So if it was decreased by 1/4, it would be 1/4 R squared, which is 1/16 R squared. So it would increase by a factor of 16. Okay, so here's question 9. Okay, so for this question, it asked a 2 kg mass is suspended on a rope that wraps around a frictionless pulley. The pulley is attached to the ceiling and has a mass of 0.01 kg and a radius of 0.25 meters. The other end of the rope is attached to a mastless suspended platform upon which 0.5 kg weights may be placed. While the system is initially at equilibrium, the rope is later cut above the weight, and the platform is subsequently raised by pulling on the rope. What is the linear velocity of the pulley the instant the rope to the 2 kg mass is cut? Okay, so you would use since it's asking for the linear velocity, you would use F is equal to mv squared over r. And trying to find v, so it would be fr equal to mv squared. V squared is equal to f times r over m, and v would be equal to root So F in this situation would be the force due to gravity, which is this mg, which is 2 times 9.8, that equals 19.6 newtons. Would be root 19.6 times the r, which is 0.25 meters, divided by the mass, which is um wait. So since it's the 2 kg into the rope, the 2 kg mass is cut, you would need it would be talking about this mass of 0.01. So it'd be 0.01 kg, and you would get 22.1 meters per second. So here's the solution right here. Okay, so that's gonna be the end of this class. I hope you all have a good weekend.